Hello. Hi. We just oh. So today we start new topic. The new topic is about all this. They all have something in common. The question is what? As you know from the lecture number 1, scientists are looking for the patterns of the nature, and a pattern is something which literally repeats itself. And what all these different systems have in common, the motion repeats itself. Of course, friction eventually makes everything stop. So if you want to make it move for a relatively long period of time, we need to apply an additional force to it. So that's what we call oscillations. And if every time, like a parent gives a push when a child is on a swing, every time you give some additional energy, that's what you call driven oscillations. So what do they all have in common? Well, a stable equilibrium position. This is a stable equilibrium position. This is this. If we deflect an object from equilibrium, the force acting on it points toward the equilibrium. If it's on another side from the equilibrium, the force acting on it still points towards the equilibrium. This force wants to restore the equilibrium. It's not always the case, of course. Not every equilibrium is a stable equilibrium. This is an equilibrium, but it's not stable. If I deflect it from the equilibrium just a little bit, the force acting on it makes it move more and more away from the equilibrium. So this is what we call a self-destruction. The nature is not like that. The nature doesn't want to be self-destructed. The nature wants to be like that. Ideally, forever. So because all these systems, all of them, have exactly the same property, we need to study the properties only one system mathematically, and that will allow us to describe all other possible situations, all of them. So, which is the easiest one to start from? A spring, because we know a lot about it. A spring experiences an elastic force when it's deflected from so a free spring has a certain length, and that length doesn't matter, as we know. What matters is the stretch, the elongation or contraction. So if I attach a 100-gram weight, it stretches. And if I attach another 100-gram weight, it stretches. But if you see, the second stretch is exactly equal to the first one. So there is a direct relationship between the force we are applying we actually can calculate. Yeah. 100 grams, 100 grams, 100 and 100, 200 grams. But that's not the force. That's the mass of this weight attached to the spring. So if you want to calculate the force which is stretching this spring, what do we do? So what is the force? What is the magnitude of the force acting on this spring right now, right here? The magnitude of the force acting on this spring. Well, the weight is the correct answer to a different question. If I ask what is the name of that force, the answer is the weight. And if I ask what is the magnitude of this force, the answer is anyone. 100 and 100, 200 grams.
2,000.
What equation did you use?
The force of gravity equation.
Force of gravity, weight, mg, exactly. But we can't use grams. So what do we have to do? So we have to convert into kilograms. 200 grams equals 0.2. 0.2 times about 10, 2 newtons. So 2 newtons stretch this spring by about 1, 2, 3, 4, about 12 centimeters. 1 Newton stretches by about 6 centimeters. And 3 Newtons will stretch it about 12 centimeters more, 36, something like that. So there is a linear relationship between the magnitude of the force we are applying and the elongation, the stretch. This is not Vx, this is delta x. And of course, if we take a different weight or a different spring, the relationship still remains linear. Different spring, same weight. If I attach this weight now, does it stretch by 6 centimeters? No. Barely, well, 1 centimeter. Because this spring is stiffer, stronger. But if I attach 10 like that, see, we can see the stretch. And we can measure this stretch now to calculate this slope. Yeah. If we have a straight graph, the relationship is linear, and we always can calculate the slope of this graph, and that slope has a name. We call it the spring constant. That's nothing new, that's a review. And the spring constant depends on properties of the spring. So that's my first real question. Just my experiment in numbers. Now, the vertical spring is a device which is similar, very similar to a horizontal spring, but to analyze a system under two forces, the influence of two forces, of course, is harder than to analyze a system if only one force is acting. A weight on a spring experiences two forces, gravity and elastic. So instead of doing that, we start from analyzing a horizontal motion, a spring attached to an object which can move with no friction, like this. Well, if you're close enough, you can see that actually I have two springs attached to it. It doesn't matter. Clearly, I always could have, if I had resources, buy one spring, horizontal spring, which I could attach to this cord and make it move exactly the same motion. It's just much easier using two springs when we make a cart moving horizontally. One spring would just wouldn't be so visible. That's it. So even if we see two springs attached to this cart, in our mind, we draw a free body diagram which includes only one. And that's what we're going to do. Almost 100% question. Well, so far, this is one of the best percentages, so I'm going to keep it for the history. 96%, I don't remember when the last time I got 96%. So I'm glad we got it. Of course, this is exactly the same calculation we've done before. Free spring, stretched spring, gravity, which equals 0.1 times 10, and the stretch, the elongation, which equals also 0.1, because we cannot use centimeters as well. So the elastic force should have magnitude, which is equal to the spring constant times the elongation. So the spring constant equals the elastic force, which also has to be equal to the force of gravity, because nothing is moving, everything is at rest. That's what we call equilibrium. In equilibrium, net force equals 0. So these forces must have exactly the same magnitudes. So the spring constant will be equal to 1 over 0.1. And we also can see the unit. It has no name, it's just a Newton over a meter. That's it, nothing else. So now, of course, if we want to stretch a spring, we have to do some work. And again, that's not a new expression. I just want to review it for the future. So it's like if I want to lift an object, my hand has to do some work against the gravity. Gravity also does work, but gravity does negative work. My hand does positive work. A similar situation happening when we stretch a spring. My hand does positive work, but the spring does negative work. This spring, only spring, will do positive work when it contracts. So when we release it, it starts contracting. And as we know, to calculate the work done by the spring, that's what's important to remember. The elastic force does this work. All we can do is just subtract two numbers. The initial potential energy minus final potential energy is equal to the work done by the spring on my hand. If by any reason we are given or we need to calculate the work done by a hand, so first we do this. We can calculate the work done by the spring using this equation, and then we can say that according to Newton's third law, etc., 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 the work done by my hand on that spring will be just opposite to the work done by the spring. So imagine that, again, only one spring is attached to this cart, and that's what's happening. That's the equilibrium. I move it from equilibrium, and I let it go. So right now, the velocity is 0. So it starts the motion from rest. So it travels towards the equilibrium, and when it goes through the equilibrium, after that, it travels further, but eventually it stops. And restoring force now makes it travel back to the equilibrium, but then it passes it again, and it stops again. And of course, neglecting friction, it should stop at exactly the same position. So this motion, which composed of 4 parts, toward equilibrium, away, back to equilibrium, and back to the initial position, that's what we call one period. One period. And of course, the position changes, velocity changes, acceleration changes, because it's speeding up toward equilibrium. After that, it's slowing down. Then it's speeding up again and slowing down again. So unfortunately, this motion is very complicated. So but still, there are things we can do about it. So we start from, I don't know, no. This is a free spring. That's how it looks when nothing is acting on it. Well, there is a cart attached to it with tiny wheels, so there is no friction. This picture demonstrates the initial situation, t equals 0. That's the initial coordinate. Of course, we point x-axis to the right. Now, where can we choose the origin? Yes?
The initial position?
Initial position. Where else can we change? Can we choose the origin? Yes. Equilibrium. Okay. Where else can we choose the origin? The stress is on the word can. Anywhere. So if I ask you where we should it, well, in that case, you would have to choose between these two choices. These are natural choices, but only one gives you clear mathematical analysis at the equilibrium. So when we talk about periodic motion, doesn't matter what kind of a system being analyzed, place your origin at the equilibrium. That's the rule of thumb, but you should follow. So now that's the origin. The initial position is, well, in my experiment, some positive number. I release it. So right here, right now, the initial velocity equals 0. And now we have to use our imagination. Let's say we wait a little and my cart is somewhere here between the equilibrium and the initial position. Now, of course, everything starts moving only after I let it go. So that's what we call the initial instant, the initial time when I let it go. And when I let it go, what forces are acting on this cart? Well, of course there is a gravity, and of course there is a normal force. They don't disappear, but what they do, what do they do? They cancel each other out, so they don't matter. So we can just cross them out. There is no friction, and my hand doesn't touch it anymore, so there is only one force which is responsible to the acceleration of this cart, and that's the elastic force. Now, what do we know about the elastic force? Well, we know its magnitude has to be equal to the spring constant times the elongation. This is the elongation. However, because we've chosen the origin at the equilibrium, the elongation also is just equal to the actual position of this cart, because it's literally x minus 0, which is just x. That's why we always have to choose it at the equilibrium. So we can simplify this equation. Elastic force equals k times x. That's the magnitude. We need a component of it. M times AX should be equal to F elastic X. That's a Newton's law. Vertical forces cancel each other out. So mass times acceleration, well, mass times acceleration is equal to net force. But relative to the x-axis, mass times the x component of the acceleration should be equal to the x component of elastic force. And if we want to write it mathematically correctly, this is what we have to write. K times x equals the magnitude, which is the positive number. But the component has to be negative. The component points to the left. So A is equal to this is the equation. That's a Newton's law for a cart attached to a spring and moving horizontally. Now, believe me or not, all other systems we've seen before described by exactly the same law. There is a variable which describes acceleration or angular acceleration if it's a pendulum. There is a variable which describes position or angular position. Yeah. And acceleration always equals some negative constant times position. This is a negative constant. A spring constant, always positive. Mass is always positive. Are you sure? Thank you. So this constant has a name and a special notation. This constant is called angular frequency. We will learn in a minute why. So the standard notation for this constant is omega. So omega squared is equal to k over m. So strictly speaking, the omega has to be equal to this. So, of course, the solution of that equation depends on these two parameters, k, the spring constant, and m. And this is the solution. So let's back up for a second. This is the equation we want to solve. Oops. Acceleration is equal to some negative number times position. That's the equation we want to solve. How? Well, in general, an equation like that is being solved by only one general scientific method, trial and error. So I'm going to give you an example how it might work. What we know from our observation, we can plot a graph for a position as a function of time. We just have to record it. Yeah. It starts from here, then position goes to 0, then to negative values, back to 0, back to positive values, and it repeats itself again and again and again and again. So how does the graph for position as a function of time looks like? So this situation, this is how. Initial, 0, well, the opposite to initial, 0 again, reaching initial, and it repeats itself again and again and again. So we just named that time interval a period. The time to make one whole motion, this time, has a name, a period. Of course, this is also going to be equal to a period, or this is going to be equal to a period. It doesn't matter how we start measuring the position. We just have to come back. Now, how many quarters does a period have? Of course, it's a quarter. It has 2 halves, 3/3, 4 quarters, 5/5. But quarters are important parts because this motion is composed of 4 almost identical parts. It goes from the maximum position to the equilibrium, and it takes exactly a quarter of a period to do that. Then it goes from the equilibrium to the opposite maximum displacement, then back to the equilibrium, and then back to the maximum. So of course, this variable, maximum displacement from the equilibrium, also has a name. We call it the amplitude. And use capital A for this amplitude. Now, how can we sketch the graph for velocity as a function of time? Go back in time. Velocity in general is equal to what? This displacement over you said something which affected the whole thing. It just disappeared, everything. But you're, okay, so, okay. A period, an amplitude, and, well, it's strictly speaking, this is supposed to be measured, calculated when time interval is very tiny. That's what we call the slope of the graph. The slope. How does the slope change? Well, 0, some negative number, some even more negative number, some large negative number, but then it goes back to 0. So here, when the object reaching maximum displacement from the equilibrium, the instantaneous velocity equals 0. Then the slope becomes positive, so positive, positive, reaching maximum positive value, and then goes back to 0 again. So this is one period of velocity. That's how a graph for velocity looks like. All we need to know is what slope means, right, from math. So of course, we could make the next step now for the acceleration. Again, the acceleration is the slope for the velocity graph. And, well, some negative slope, then the slope gradually decreases to 0. Okay. Then it becomes positive, reaching maximum slope, and then gradually goes to 0 again. And here, again, reaching maximum negative value. So something like this. So if you look at this graph and at this graph, they're very similar to each other. Basically, what do you need to do to that graph to make this graph? First, you have to flip it, and then you have to either stretch it or squeeze it, and that's it. And that's exactly what mathematically it means, multiplied by a negative constant. So this is kind of a proof that the solutions for our equation should be some kind of a harmonic functions, like a cosine or sine. And in general, this is how can we write it down. This coefficient A, that's the maximum displacement from the equilibrium. This coefficient tells us how many oscillations happening every 2 pi seconds. So this is the number of complete motions in 2 pi seconds. So basically what we need to do is take one period and multiply by 2 pi. So this is the relationship between what we call a period, a physical quantity which is easily measured, and this mathematical quantity which we call angular frequency. Remember, if we know a period, 1 divided by period has a name. How do we call it? Frequency, just regular frequency. And we know that there are 3 different variables people use for a regular frequency. It doesn't matter which variable you want to use. When we talk about circular motion or when we talk about rotational motion, most people would use this or that for the frequency. When we talk about oscillations, most people use a lowercase f. So you can use anything else. So this is the relationship which relates a regular frequency, number of oscillations per second, and that this mathematical object, angular frequency. Well, of course, again, in math, there is no difference between sine and cosine, so we can replace, it just changes the constants inside. Yes?
Can you just rewrite that main equation?
No. I'd rather switch to the slide where it's written. So the equation I had written looks like this, but as I just mentioned, mathematically, it doesn't matter if we use a cosine function or a sine function. We'll learn soon that for some specific situation, using cosine is just easier. For other specific situations, using sine is just easier. So, and this is also terminology we use. This whole combination inside the parentheses we call a phase. Sine has a phase, cosine has a phase, everybody has a phase, sometimes many. And of course, when time equals 0, 0 times anything is 0. So this constant has a name, the initial phase. Normally, we always can choose it to 0. This is what we should call, well, depending on, this variable has no special name, but it's related to initial positions. So in a minute or two, we'll learn how. And this is how a graph for any motion like that looks like, in general, looks like. My graph started from maximum because that's how I made it move. First I moved it, and then I let it go. And of course, it never goes beyond that initial point. So in this situation, the initial position automatically equals the maximum displacement, which is amplitude. There is another way to make it move, starting from the equilibrium, right? But now we can give it a hit. Of course, now the initial position equals 0, but initial velocity is not 0. And in general, graph might look like that, something weird. But if we shift the axis, for example, in our mind, we can start measuring time, not from this instant, but from instant a little bit before that. So if we shift the graph, the axis slightly to the left, and this axis up, we always can make it look like any standard cosine or any standard sine. And if you look at this graph again, this arrow represents, or this arrow represents one whole period of the motion. And here, from this reading to that reading, we should include exactly two amplitudes. One, so the equilibrium positions is in between. The person who did this graph didn't set the equilibrium position to the origin. That's why it looks weird. But we always can reset it if we want to. We know that the equilibrium position is here, and the distance from equilibrium to the maximum displacement in either side should be equal to 1 amplitude. So here we have exactly 2 amplitudes. Okay? Now, we saw the graphs for position, velocity, and acceleration. And this is how each graph can be written mathematically. If the position graph is a cosine graph, in that case, the velocity graph will be a sine graph, and the acceleration graph will be, again, a cosine. This product has a name, maximum speed. That's the maximum value the speed might have. This product has a name, maximum acceleration. That's the maximum value for the acceleration which this object might have. And this is how different parameters affect all these all this motion. So this is about 250 gram cord. 1 Mississippi. So the period of this motion is about 1 second. Now, if I make it heavier, clearly the period changes because it's more inertia. So this bar, each bar, also equals 250 grams. So now the whole mass of the system is 4 times the initial. 4 times the initial. So 1 Mississippi, 2 Mississippi. So now period is 2 seconds. We quadrupled the mass, but the period is only 2. If you make the mass 9 times heavier, the period triples. So the relationship between mass and the period is not direct. It's a square, or a square root, depending on how you write it. And it's exactly here in this equation. If you combine these two equations together, you just replace the angular frequency with the square root of spring constant over mass and simplify. That will give you a relationship between the period of the motion the mass of the object, and the spring constant. So if you're increasing the mass, you're decreasing, you're increasing the mass, you're increasing the period, you're decreasing the frequency. But if you're increasing the spring constant, it moves faster, so you're decreasing the period. And to see that clearly, all you have to do, just rewrite it. The period equals 2 pi square root m over k. Well, all right, I'm going to ask you this question. I want to. I don't know why. I have a feeling it's important to ask right now. So, you can see the pattern. So you can know what button to press depending on your choice of the answer. T over 1, press 1, T over 2, press 2, T over 3, press 3, T over 4, press 4, T over 5, press 5, etc., etc., etc. So it takes one period, T seconds, to make one whole motion. How much time does it take to travel this particular distance? Okay? So write it down and keep pressing. I'm not going to ask this question. This question I want to do together with you. So this is a situation when only a portion of a graph is presented. A portion of a graph. But still we can use it. For example, is this a period? No. That should be exactly a half of that. So if we say that, a half of the period equals 12 minus 4 seconds. 12 minus 4 is 8. So hence, the period should be equal to 16 seconds. Now, what about amplitude? Is this the amplitude? No. The amplitude should start at the equilibrium. This is from one maximum to the opposite maximum. So this is equal to how many amplitudes? 2. That's 2 amplitudes. That's it. So 2 amplitudes should be equal to 9 minus negative 3, which is 12. The amplitude should be equal to 6, whatever it is, centimeters, meters, assuming international system of units, meters. So we can say immediately that the motion equation for this object should be equal to, well, this times, let's say, cosine of the period is 16. The angular frequency is equal to 2 pi divided by the period time plus the initial phase plus some constant. We don't care about these constants because in many situations we can set them to 0. T is a running variable, x is a running variable. Why don't we care about those constants? Okay, so interestingly, exactly 50% said 1. So T over 2. Let's go back up for a second. 1 amplitude. Again, this whole question boils down to another question we've answered before. How many quarters in one period? How many quarters? 4. Not a tricky question. So how many amplitudes does it travel in one period? 4. So to travel 1 amplitude, it needs a quarter of a period. To travel 2 amplitudes, it needs 2 quarters or a half of a period. To travel 3 amplitudes, it needs 3 quarters of a period. And to travel 4 amplitudes, complete motion, it needs 1 whole period. So These are two distinct specific situations which we're going to talk about. Number one, an object is released from rest. In this situation, well, it's either cosine or, if we release it from the opposite side, minus negative cosine. Initial speed is 0. Initial position is equal to the amplitude. And another extreme specific situation is when the object is at the equilibrium and we hit it. In this case, position graph starts from 0. How does velocity point? Well, it depends. If I hit it to the right and my positive x direction is to the right, initial velocity points to the right, so the graph should go like this. That's what we should write. But if my positive x direction points to the right, but I hit it to the left, my initial velocity should point to the left. So the slope of this graph should be negative. So the graph should go like this. In that case, we choose minus a times sine. That's all we need to know. And what's happening to the energy? So I'm going to go to those problems as soon as possible. But first, what is happening to the energy? The energy also changes in time, but energy also changes in space. So if this is the expression for potential energy, this is a parabola, a quadratic function. So this red parabola represents the potential energy of this card as a function of position. How does it change in time? Well, the position equals this, so we square it, and we plot the graph, and that's going to be something like this. What about kinetic energy? Well, for the kinetic energy, we have two options. We can use this expression, but it's easier to use the law of conservation of mechanical energy. You see, it's written at the bottom of the slide. If there is no friction, mechanical energy stays the same. So, if you want to calculate the kinetic energy, all I need to do is just take the total energy and subtract potential. So that's how it's done here on this graph. Kinetic energy is equal to the total energy minus potential energy, which is equal to a fixed number minus this expression. This is also a parabola, but branches you should look down like this, because it's a negative coefficient. You can rewrite it like this, plus a constant. Now, what about total energy? Can we calculate it? Of course we can. We can use any expression, because when this cart reaching maximum displacement, it stops instantaneously. So here and now, kinetic energy is 0, so the potential energy becomes equal to total energy. So total energy is equal to k times amplitude squared over 2. What about equilibrium? Click. When it travels through the equilibrium, x equals 0, no potential, only kinetic. So at the equilibrium, the total energy is equal to maximum value of kinetic energy, mv maximum squared over 2. All right. Now you're ready for the lab, and on Wednesday we're going to do some problems.
So you said that the whole system reaches its maximum potential energy at equilibrium.
No, kinetic.
Yeah, that makes sense. Thanks.
Yes.
I sent you a quick email about the attendance too, or response rate. I just want to make sure my response rate is I got like full credit on the first one, but I need a. I just want to see. I know response is a hassle, but.
You're using the response verb. Well, we can check it right now if you want to.
Okay, yeah, that would be great.
I'm gonna.
Do you need the ID?
No, you need your clicker.
Okay.
This is the session ID for you right now. 61865. Six. Yeah. So you should log in the session. When you're ready, you can tell me so I can start the question. Yes.
I wasn't here on Friday. I missed discussion in lecture. Covering my discharge papers, can I get
For the lecture, you will get it automatically. For the discussion, it depends on how many. If it's the first discussion, you shouldn't bother. If you missed before, or you may miss in the future, in that case, I would advise to make it up.
Okay.
So it's up to you, basically.
Make it up now.
Well, now you can't. You have to send me an email because I can't do it right now.
Okay.
So we could.
Should I just send you an email?
Yes.
With everything? Okay. Thank you.
So you're ready, right?
Yep.
So let's see. And
Yeah, it's working. Just anything.
press something.
Okay.
Just a second. What do you want? This is what I want. Your name or the name should be fine.
On my name or the
Just your
okay.
Just your name.
Let's fix it.
Okay, now we see it. Okay. You should go set. And it might in the future again be some discrepancies, but we always can check it.
Okay. All right. Awesome. Thank you.